Thank you for joining us for today's regular monthly GPSX webinar. Today we're going to be talking about how to model dissolved air flotation systems, or DAF systems, in GPSX. The DAF model is one that doesn't get used quite as much as a lot of the other unit process models that we have in the software, but we do get semi-regular questions about it, and we hadn't covered it on a webinar before, so I thought it would be a good time to take a look at the model since it is kind of interesting and related to our clarifier models, as you'll see when we go through the webinar here today. So, as per usual, I'm going to spend a little time showing you a few slides and running a few simulations and so on. If you have any questions as we move forward, please feel free to type those into the chat or the questions box that is available. Excuse me, I should open that up so I can keep an eye on that. There we go. Type that into the chat, and we will answer those at the end after I've gone through the whole webinar. What I usually do is hang around and answer, 4 or 5 questions that might come up along the way. All right, so here's the plan for today. I've got a few slides. I want to talk a little bit about the dissolved air flotation system, just in general, if you're not familiar with it already. And I'm going to talk about the one-dimensional solids flux model that is used to mechanistically model the DAF unit. And as with all unit process webinars, I want to go through what all the parameters mean. And specifically, I want to talk about what are the ones that affect the calibration. So you know sort of where to go, things that you might want to adjust as part of your model calibration when you're using the DAF model. And as always, it wouldn't be a Hatch webinar if we didn't have some desktop demonstrations. I'll be running through a couple of those as well. And then, as I mentioned, we'll do some questions and answers at the end. All right. So, dissolved air flotation is a fairly commonly used solid separation process. I've seen it both in a municipal wastewater treatment and also industrial wastewater treatment as well. It has some really specific applications in the industrial world. Basically, what happens is you have a tank. You are feeding your solids into it through the flow of your influent, and you're also at that same time feeding a supersaturated water, supersaturated with air, such that when it comes into the tank, and that tank is equalized in terms of pressure with the atmosphere, that micro bubbles will come out of solution immediately and form in the tank that you have. And then those bubbles will, of course, rise automatically, and they'll capture the solids and other things as it goes, and then carry those to the top. And then usually there's some sort of conveyor or scraper that will move and take along those floated solids and remove them from the surface. Now, this is used in a couple of different contexts. You can use it for removing solids. You can use it for removing oil or fat, oil, and grease, and other types of non-solubles. There's lots of different applications of this type of technology. Now, I wanted to go through and sort of highlight the, practical applications, talk about some of the technologies. There's a very, very wide range of different types of scales of this as well, of this type of technology. So rather than try to cover them all, I'm just going to show you a couple of the most common ones. These are units that are designed to either be sort of running at full scale. I saw lots of really interesting things about sort of pilot scale, mobile type facilities that can be used as well. They're all generally kind of work the same concept. You have a reactor here, as I mentioned. You have a way to inject the air and create the bubbles. And then you also have a collection of solids at the bottom, and then most of the solids will be captured by the bubbles floating to the surface. And as you can see, there's usually some sort of conveyor thing moving the solids off of the top of those as well. Now, normally a DAF system is not just the DAF, actual physical DAF unit by itself. It typically has been preceded by some sort of chemical treatment system. So you're probably going to be adding a coagulant to be able to sort of flock and gather the solids into as large a flocks as you possibly can. So you might be adding something like PAC, or you might be adding ferric chloride or something. And so in those ideas there, they may affect the pH, and so therefore you may want to have some other chemicals there to control the pH, keep it in the right neighborhood. And then also typically you're adding a polymer to sort of assist with and improve the performance of the, attachment to the solids to those bubbles and get, a very maximum amount of the solids being captured and taken up to the surface of the DAF unit. Now, the coagulation and flocculation typically happens actually upstream of the DAF unit itself. There's sort of these long tubes that are there. There's sort of long plug flow systems that are there to do mixing and coagulation. And so those are typically immediately prior to the DAF unit. And so rather than talking about sort of all of the different parts of it, I'm just going to stick to talking about the DAF itself. So the solid separation and the flotation part of it in today's webinar. Now you can do all of those other things as well with other units in GPSX. So they would just appear upstream from the DAF unit in the process flow diagram that you've put on your drawing board. Right. Okay. So a one-dimensional flux model is used in the DAF model, and it is there to sort of do a mass balance of the solids and all of the layers of the DAF and get some sort of fairly predictable, sort of a good predictive kind of performance out of the model. And in this case, when you want to use a DAF model, you go to the biosolids treatment panel on the left-hand side of your drawing board, and you'll find the dissolved air flotation unit there. So drag that on the drawing board. So just to really highlight what's going on here, this is normally the upper left corner is where you attach the wastewater input coming in, whether that be sort of a mainline influent, or maybe you're doing it to separate some higher solids from your solids handling side. It's in the biosolids treatment section, but there's nothing saying that you can't use it for, other types of treatment as well. It's just happened to where we put it amongst the other solid separation units. So we have the wastewater input coming in. You can see these bubbles here. They're going to float the solids to the surface. This is where the connection point that is going to be bringing off the high concentration of floated solids at the top. And then the effluent or subnatant in this case is going to be coming off the bottom layer and comes out of this connection point over here. I'll take a really quick moment to mention that we do have this connection point over here, even though I'm not really going to be using it today. This connection point is for the supersaturated water that you would be theoretically adding. Our original version of the DAF model didn't have this, and actually it was just the 3 connection points. But we had a project where the amount of water being added to deliver the air that was going to be creating the bubbles was actually not an insignificant amount of water. So we actually had to, for water balancing reasons, include it. So now that doesn't mean you need to use it, and it doesn't actually really have any effect on the performance. It's really just there for bookkeeping, for record keeping. If you really care about the amount of water that's being added, then you can actually add this here, and then you'll get a little bit more flow going out if it's something where you need to keep track of the amount of flow. Right. Okay, so that DAF model is a one-dimensional flux and is very similar to the one-dimensional clarifier models that we have in our primary and secondary clarifiers. So just to briefly refresh your memory about those, basically it's a 10-layer model. So we have what are essentially 10 reactors stacked on top of each other like this, sort of pancake style. And we're doing a mass balance around each one of those layers. And so the feed layer is where the solids are being fed in. There's a liquid motion. That is, of course, the water coming in, advectively carrying the solids with them as they go up and out or down and become part of the RAS and wastage. And then you also have, at the same time, the actual mass balance of solids of it just falling from one layer to the next. That's a settling process. And so we do a derivative and we do our mass balances around that for each one of the layers. Now, you can, if you want to get into that in more detail and sort of really dig into the details of how this all works, I recommend that you go to our YouTube channel and watch the Modeling Clarifiers in GPSX webinar, where I use this image and I go into a lot more detail about what's available for you on the clarifier side. Okay, so for the DAF, it is essentially the same concept, except we have flipped it over. So we're using the same approach, and we're using actually a very similar set of equations to describe the flotation as we did the settling, except now they go up instead of down. So basically, we're going to have that same idea where we have an influent coming in, and that goes into a certain feed layer. We then have the solids being taken from the top, that is the scum being removed from the top, and then we take our effluent from the bottom layer. And that same process is being used here. We have some flow going up, and we have a lot of flow going down. Most of it is going to go down and out through the effluent. And then we, of course, have our flotation as well. So in this case, we're using an equation to describe what is the amount of solids that comes out of the second layer and into the third layer, et cetera, as these things make their way up. So same concept. And basically, we're doing a mass balance around each one of those layers and getting prediction of the solids concentration in all of them. And then therefore that tells us the concentrations in the two connection points that are leaving the model. Right. Okay. So we are using a double exponential model for our flotation in the same way that we use the double exponential model for our settling too. So just as a really quick refresher, again, the double exponential model is something that relates settling velocity to concentration. So depending on what concentration is in your layer, we can tell how fast the solids will settle out. And it is generally a relationship that looks like this. And so the lower the concentration, the higher the concentration, the lower the settling. So we're doing it the same way, but now we're talking about flotation. So I've got floating velocity here. So in the upper layers where there's a lot of solids crammed together in that layer, they don't go up as fast in that sense. So now it's a double exponential model because it looks like this. So you have two terms, the yellow line and the red line, and we subtract them, and that gives us this blue line. That's the actual shape of the flotation curve that we are going to be using. So there's kind of like a sweet spot over here in the concentration where it floats at its sort of maximum level. But as it gets up and it starts to get condensed at the top of the DAF, it floats a little bit slower rate. So, and then just like our clarifier models, we actually put a cap on it, a maximum floating velocity, and there is a minimum amount of solids that are required to do any sort of flotation at all. So once we apply those two to the green line, it ends up with a curve that looks like this. So it's the exact same approach as we are using otherwise, and now we have what we need to do our mass balance around each of those layers. And then you have the ability to adjust some of these parameters in order to change the shape of this curve if you would like to be able to do that. Okay, so that's the part that is essentially the same as what we're doing in our clarifier models. So, and then now what we're doing is we're going to, I'm going to talk about two major differences from the model. So one of them is that the flotation parameters themselves are modified by the operational settings, right? So, and it is really some of the ways that they float to the top is a function of the solids properties themselves. And those are menu items that we have, items that are on the operational settings menu in the DAF unit. So I guess what I'm trying to get at is the density of the solids as they form the scum on the top actually plays a role in how fast that they can gather up there, right? So there's that's a little bit different than our settling parameters in our settler model, which kind of we sort of treat them as if they're independent. And then secondly, this is actually the more important one. The removal of solids from the top layer is actually predicted from the operational settings. So in other words, you don't set the rate at which the solids are being removed. It's actually predicted from the model. So we have a flow coming in and we have a flow going out, and then the remainder is our effluent, our clean water that's coming out as the subnatant. So that is very different than the clarifier model where we set the RAS, the underflow flow rate, and then of course the wastage flow rate. But then here, we're not actually setting any flow rates. They're predicted by the rate upon which we can move things, out of the way to which that scum can be removed off of the top. Okay, so that's a very wordy way. I think it's maybe a little easier if I describe it this way. So as the flow comes into the DAF unit and it's distributed in the layers and it's bringing all of the solids up to the very top, we use the parameters that are in the menu to determine what the scum concentration is going to be at the top. It's a property of the air to solids ratio. It's a property of some of the details that you can put for the scum and so on. And there's some calibration parameters as well. But nonetheless, what you end up getting a prediction is how dense that scum is going to be. And then from that, and some of the other parameters on the menu, we calculate what the flow rate is going to be as it comes off. So we now have a concentration and a flow. And then now, since we know this flow and we know this flow, we can calculate this flow down here. And so we basically are saying that whatever isn't taken off here, the rest of it is taken off at the concentration that is the lowest layer down there. And then, of course, you've got your layers in here. So now this is a completely nice mass balance all the way around. Okay, so that kind of tells us how we're going to operate this model. So you're going to have the loading coming in, you're going to have your properties of everything, and then it's going to predict the effluent concentrations and the split up of the flow coming out that side as well. Now, I should take one moment here to point out that many DAF units also have settlable solids being removed from the bottom. Now, we don't have that in our model, and it's actually on our list of things to add to this model at some point, possibly for the next release of GPSX. So if you're in a situation where you know there are being solids removed from that influent flow that's coming in and they're settling out and going down, despite the fact that the bubbles should be there pushing them up to the top, but they're heavy enough that they fall out. You could very easily put another solid separation unit right in front of this one. Just grab that black and blue generic dewatering thing and just remove off a bit of the solids there and put the rest of it in here and go that way. We're going to combine them together at some point, but for now, that's how you would treat that issue. Okay, so now moving on to the parameters. These are the important things that you need to know when you're setting this up and calibrating it for the first time. When you right click on the object, you go to in the middle of the object, go to the input parameters menu, and then you can see the usual type of menus that you would expect to see in a GPSX unit. The main two that you really need to think about, three, I should say, a physical, operational, flotation. These are the ones that I want to talk about today. So obviously the first one is the physical menu. So just like any of the other GPSX units, basically we're just specifying what is the size of this thing. So we're looking at the surface area. What is the surface area on the top? And then what is the height here? And then what is the feed point? That's basically where the flow is coming into here. So as I was going, if you want to go back a couple of slides and take a look, again, that was the layer into which the solids are being injected, that they're coming in from the influent. You can specify that here. Just give it in meters, we figure out what layer it goes into. Okay, that's pretty straightforward. Now, this is the one where we have operational settings, and these are the ones that are where you will touch up the calibration of your model. If you're running your DAF model and you find out that the scum is too high or too low a concentration, or the removal rate is too good, then you can adjust some of these parameters to calibrate your model and get it to behave the way that your DAF unit actually does. So let's start with this setting right here. Basically, the way to calibrate it is to look at the performance versus the polymer dosage. That's essentially the biggest dial that you can dial in the most straightforward way. And it's relatively intuitive to understand. So basically, there are two numbers right here, 2% and 5%. These are the dry material content of the scum or the floated solids at the top. That's kind of like the value that you are setting. You're saying, I'm going to have solids that come out at this concentration at the top. And you can basically gives you two set points that you can work with. That is your relationship between polymer dosage and the dry and the scum concentration. So one of them is for no polymer dosage at all, and the other one is for the optimal polymer dosage. So what this is saying is, and by our default setting, is that while we're running our DAF, depending on where we're at with various parameters, our solids at the top of the DAF are going to come out at either like somewhere between 2 and 5%. So 20,000 to 50,000 milligrams per liter. Now, what is this optimal dosage? That's this setting right here. This is grams of polymer per kilograms of solid. right? So 0 gives me 2% solids, and if I put my polymer dosage at 20 grams per kilogram, then I get 5%. So by adjusting these things, you can change the shape of that relationship as needed and calibrate your model. And then when you get to the point that you're actually applying the polymer dosage, then you're saying this is how much we're actually using, then it just tells you where you fall on that line. So basically, if it's this kind of linear relationship, so here from 0 to 20, that's that number. We're going from 2 up to 5% solids, and wherever we're doing that dosing will tell us where we fall on this curve. Now, I know in reality, of course, that's not a completely perfect linear relationship, but this is the relationship that we've used actually for many years, and it works nicely so that you can very easily and understandably calibrate your model. Okay, so that's what allows you to change either the up and down location or the slope of this line by changing these parameters. Okay, now there are a couple other parameters on here that are worth talking about too. That's basically your air to solids ratio. And so that is basically going to help us determine, once we've got a concentration, what the density of that is and how we get to a flow rate. So that is actually something that you can set either to an optimal value. It's actually set to the optimal value as you are here, and then you could calibrate the model by reducing this down a little bit to be less than optimal if that is the case. Okay, so I'll come back and I'll show you sort of the sequence of calculations as it happens. Right. Okay. So we're going to move on now to the third and final section here. That's talking about the flotation parameters. Now, if you've used GPSX before and you've used our clarifier model, you'll recognize a lot of these parameters. So basically, what we're talking about here is, instead of a settling velocity and our hindered and flocculent zone settling parameters, we now have a maximum floating velocity, and we have hindered and free floating parameters instead. So they have exactly the same meaning. Those are the terms that were in that equation that I wrote across the top of the screen here a moment ago. They work the same way. You can calibrate them exactly the same way that you would in the clarifier model. So now this is going to control not just what's going on in the top layer, but actually how the solids are being floating up and down and how quickly they get up to the top based on these parameters that you have set here. We even have a non-floatable fraction, just like we have a non-settlable fraction in the clarifier, and you can set that here too as well. And then lastly, we have these other parameters here that are to deal with the air to solids ratio and the calculation that takes us from concentration to a flow rate. And so they can be adjusted as well. Okay, so I want to just touch on what are the things that you can output before we move along here. Oh, hang on. Just let me see. I just want to make sure I didn't skip over the one slide that I was looking for. This slide. That's the one I was looking for. All right. So in this case, now I can sort of explain to you how the sequence of calculations happen. So you get the influent flow coming in, we get our distribution, we have some solids moving up towards the top. When you get to the top, then we're going to use those parameters that I was mentioning before, like how quickly it floats up is the flotation parameters that I just showed you. What concentration it gets is determined from the polymer, as I mentioned at the top. And then we use those air to solids ratios to get this thing over here on this calculation. And then that allows us to calculate the other flow. So it's basically just a sequence of events, a sequence of calculations that takes us from loading to concentration to mass loading, leaving the system. Okay. So back to what I wanted to demonstrate here. These are the outputs that you can get out of the model. So just like the clarifier and the SBR and any of our other sort of layered models, you can plot the suspended solids concentration in a vertical sense in the model as well. So you can go here, right click in the middle of the DAF unit, click on output variables, and click on suspended solids, and that will give us this menu here, and you can see the concentrations just like you would in the regular clarifier, and I'm going to show you an example of this shortly. You can see, of course, it's the lowest concentration is at the bottom because we're floating the solids up, and here at the top we have our target value that we had of 2% solids. You can actually use this on a horizontal bar graph, just like we do for the clarifiers, and I recommend that as kind of a nice intuitive way to understand what's going on in your system. You can also go down here to the DAF variables menu, and you can see a bunch of other things that are related. These are, again, like our settling parameters. You can do things like upflow and downflow rate and the floating velocity and whatnot. These are kind of more detailed parameters that may or may not be useful to you, but I'll just let you know that they're there. And lastly, from the overflow connection point, so right click on that connection point, output variables, there's a little bit of, the dry solids material content, and then mass flow. So this is mass per time of the amount of scum being taken off. That might be helpful to take a look at. Okay, so now it is time. So let's do the desktop demonstration here. Okay, so this is GPSX, and so rather than show you a whole full plant model, I'm just sticking to showing you just this particular unit process today. And so I'll just very quickly point out, if I right click here, if you kind of forget what the connection points are, you can always go to the labels menu down here, hit labels, and you can see what each of these things are. So this is the floated solids, this is the subnatant, etc. So let's go over to simulation mode. Let's run a steady state solution. And since that's the only unit on the board here, it comes to steady state pretty quickly. And if you go to the quick panel, you can see all of the details. So here I'm showing flow, and you can see the feed coming in, and this is our calculated flow leaving at 2% solids, 20,000 milligrams per liter, and all the rest of the flow is coming out here as the subnatant. And there on the effluent, you can see the solids are just under 100 milligrams per liter. So there's a couple other kind of design parameter stuff that might be of use if you want to take a look here. When I was setting up this example, I was using some of this to make sure I had a realistic residence time. So if I click here, I can see it's 43 minutes. Residence time in this particular unit. We can look at things like hydraulic loading rate and so on. I was looking at, where is it here? Gallons per feet squared per day, 2,500 roughly. So these are all kind of numbers that might be useful to you, and you can display them in either in metric, like SI or imperial units if you like. Solids capture rate is always kind of a very handy thing to keep in mind. You can watch how this changes. And then also that mass flow of solids being taken off the top of the system is also that number here. So I'm going to leave this in this position so we can see all these numbers as we go. Okay, so now let's talk about the polymer dosage, for example. So I took the parameters that I was showing you in that explanation before off this menu, and I put some of them up here. And just to refresh your memory here, our optimal polymer dosage is 20. So we're going to go from sort of, this is the amount that I'm dosing, and it's going to go between 0 and this optimal level. And that's going to take us from 2 to 5% solids. So I'm going to start by jumping up from, okay, first of all, let's just look at it with no polymer dosage at all. And we can see we have 2% solids, right? So I'm going to jump up to doing 8 grams per kilogram, and then I'm going to run steady state again. And then now we can see here that 20,000 jumped to 32,000. And now this has decreased. This was 41 meters cubed per day before, and it's dropped to 27. So what does that mean? That means we have denser solids at the top now. So we're actually taking out a little bit more of the in terms of mass, even though this has come down. We're removing it. It's basically the polymer addition is make the whole process more efficient, right? So I'm going to jump it up again to 20, to that maximum. So we'll take it up to that optimal polymer dosage. And I'll run that again. And then you can see here now we're all the way up to 50. That's exactly as we expected from this setting right here. And so now you can see this has dropped all the way down to 18. That was 41 to 27 to now 18. And we have our very dense solids on the top, and it's performing very well. Previously, our effluents TSS, if I look at that number right here, that was 100. Just under 100 when we started. It's now down to 45. So the polymer addition is doing a better job of removing these solids as we go. Our solids capture has moved up a little bit with that dosage. Now, you can actually move it past optimal. Like if I make this 50 and just keep going, basically nothing happens. Why? Because basically it's reached the optimal. Adding more polymer is just wasting it. It's not going to make things better. It's reached that point, where the optimal has been had. Okay, I'm going to go back to 8 again. I'm going to reset back to a little bit of polymer dosage, and then I do want to show what happens when you run this dynamically. So let's take a quick look here at this DAF profile. So what I did was I opened this menu here, output variable, suspended solids. This is the one that I was mentioning before, and I dragged this over here onto this graph, and I selected output graph type. I picked the horizontal bar chart, so that makes it so that this is the top of the DAF unit and this is the bottom. So when we run this, we get predictions of concentration. So here's our 20,000. But you can see in all these other layers, we can get the details of the predictions of all of those. This is going to be our effluent concentration at 65 right now. Okay, and now I want to run a dynamic run just to give you a sense of how this behaves very similarly to the clarifier. Now, the scum at the top doesn't behave the same as a sludge blanket height because we've done all these changes. That's why we have these features in here to relate it to density and so on. So we're trying to make it realistic in that sense. And so you'll see this concentrations change around. So I'm going to run a 30-day simulation, and I'm also going to just give it a bit of a delay because otherwise it'll go by so fast I won't get to tell the story. So, all right. So, and I'm going to change the influent flow here. So keeping this concentration the same, we're just changing the flow rate going through. Okay, so if I just start moving this thing around, you can see, as you would probably expect, that the amount of solids that are available in the system are changing and the concentration's going up. So if I really increase this as we go, we can see the scum at the top kind of keeps going up. But then eventually it's kind of get to some point where just increasing it doesn't make it any better. So any higher, right? So when we're over here, you'll notice now we're at this maximum number. It's never going to go above 50 at this point. So that's one of the parameters in the model, is sort of the maximum rate at which you can get the scum off the top of the system. So if I max that out, right, then you'll see that the rest of the layers just start to increase. So if I click down here, we can see that here. Let me just start over again so that we can do this in a way that makes sense. Okay, so I've clicked on this bar down here. This is the effluent concentration. And if I just keep knocking this thing up here, eventually it gets to the point where it can't remove the scum fast enough anymore to keep up with the loading. And it doesn't get a higher concentration at the top, but the effluent concentration just keeps going up as I load it more. So it fails in a different way, I guess you could say, than a clarifier does. Well, I guess it's similar way, but still, it gives you a sense of a way to do a capacity analysis on your particular unit based on doing that kind of work. And of course, you can do that at whatever polymer dosage that you like. Okay, so that's a sense of this. It's a very simple solid separation unit. And so it is not. It's got some sophistication in the sense that we're doing, the removal of the solids at the top in a kind of unique way to try and make it more realistic to what happens in a real system. Okay, so I want to just take one minor detour here before we wind things up and just mention the API separator. It's not the same thing as a DAF, but it's close enough that I thought I would mention it. So now, for those of you who are familiar with the petrochemical wastewater library in GPSX, we also call this Mantis IW-lib, Mantis Industrial Wastewater Lib, a library. If you flip over to that library, Mantis IW is now included in all GPSX licenses as of the last release. And so you'll notice that we have a different set of unit processes. And one of the ones that's unique to the petrochemical industrial library is the API unit. So you'll find it here on the primary treatment unit. And in fact, the DAF is also found in the primary treatment unit there because it's a little bit more appropriate to be used in that sequence of your process flow diagram. And the API unit kind of works the same way. Now, there's no air being added. There's no dissolved air. It's just basically doing phase separation in this case, and actually some solid separation as well. So the wastewater comes in, there's actually some solids being taken off the bottom. We are removing oil at the top here. So that's another connection point where the oil that we'll be modeling comes off. And then, of course, the effluent water that is being treated will come out that side as well. Now, the reason that it's only in the Mantis IW library is because that library actually has a state variable for oil. And so we can use that there. We don't really have that in our other libraries, and so you won't see the API unit there. Now, if you really want to get into doing the industrial side, if that's the thing that you focus on, then you may have come across this already. So it's an interesting unit in the sense that it is not layered. It's not a mechanistic model in the way that the DAF model is. In this case, what we're doing is we take the physical dimensions of the unit, and then we have some flows in and out. And what we can do eventually is just get a overflow flow rate. We can basically get a flow rate of the water moving through the system, and then some properties of the oil are specified in here as well. And then from that we can calculate the rate at which the oil can be separated. It's the size of the droplet and many other things that are used in that calculation, and then from there we can calculate what oil gets recovered. So, but it happens instantaneously. It's not a mechanistic model. Right. Okay. So I'd like to just show you that really quickly. So just let me back out of here. And if you go to the sample layouts menu, we actually have an industrial wastewater example. So, and it's got the API unit in it. So I'm going to open that up. I'm just going to run it to steady state here. So it takes a second here as we switch from one library to the other. Here we go. There's that API unit. So just before I run steady state, I'll just show you what the units look like. So there's a physical unit. You know, what is the size? It's more or less the same type of dimensions as you would have in the DAF. This example also has a DAF in it, by the way. And then we go to the operational unit here. And so you can see that we set some flow rates for removing the solids off the bottom and whatnot. And then here, estimate oil removal efficiency. Either you can set it yourself or you can estimate it from these other parameters, including the size there. Basically, we're just calculating how fast the oil can be removed based on its velocity, and then you can put that against the velocity of the water and then figure out a ratio of the oil that gets removed that way. So let's put that over here. Let's run this simulation. And if I double click on that API unit, you can see here that we're getting essentially 5 milligrams per liter being removed through the oil. And if I go to and click on that connection point and I go to display the concentrations, I can page through, find the oil, and I can see that concentration right there. So just something slightly different, a little bit out of the ordinary, and it's close enough to the DAF that I thought it was worth mentioning. Okay, back to winding up the slideshow here. Okay, so the DAF unit or DAF technology is a fairly commonly used technology in both municipal and industrial wastewater treatment. As I mentioned, in industrial world, it's probably removing more than just solids, as you might find. Our DAF model is, a fully mechanistic mass balance based model, similar to the clarifier settling model. Uses many of the same approaches. Many of the parameters have the same meaning, even though it's operating in the opposite direction, up instead of down. And we have essentially modified the model, especially in that top layer, to have a way to calibrate the model for performance versus polymer dosage. And by doing that calculation at the top to get to a certain scum concentration at the top of the unit.